So today's class is 3D scanning and printing. We're going to alternate for a few weeks. Next week, back to electronics. Week after that, back into machining. And Adrian points out I'm not sharing this screen. Now I'm sharing the screen. Okay. So this week we're going to scan and print. Then we're going to alternate. Next week you'll design electronics. Then you're going to do large format machining. Week after that, you're going to do produce electronics. You might have thought this was a class in 3D printing, the whole Fab Academy. This week is about the strength, but also the weakness of 3D printing. 3D printing is powerful, it's important, but it's only one of multiple fabrication processes. And so you'll be meeting things that can make things bigger or stronger or faster than 3D printing. Within that range, 3D printing has a very important role in complexity of geometry. So this isn't just about how great 3D printing it is, it's about understanding how 3D printing relates to all the other processes we'll learn about. So subtractive machining dates back to 1952 at MIT with a tool that cuts. There are many different claims to inventing 3D printing. This is one of them for stereolithography. There's maybe 5 other claims to inventing 3D printing. They all have to do with computer-controlled deposition. So why? This is a 3D printing hobbyist in Switzerland who's done beautiful work making things like this is an all 3D printed clock. So one of the main strengths of 3D printing is just the geometrical complexity of what you can produce. This is a nice project that's 3D printing flexures, things that deform to make microscopes. This comes out of the Kerala lab. This is an all 3D printed milling machine. So you're going to make little circuit boards. This is 3D printing the machine to make the circuit boards. So what's good about all of those examples is complexity, in a sense, is free. It takes about the same time to make a complex geometry as a simple geometry. So it opens up design space. A second one is because you're printing, you have access to the internals. So if you want to make like a nested part, like an axle that fits through a sleeve, done conventionally, you need to make them separately and fit them together. With 3D printing, you can actually print the nested part right inside the thing around it. And third is it's roughly net shape, meaning there's, depending on how you print, there can be typically some waste material, but you're not removing a lot of waste material. You're roughly putting material where you want it, and so you reduce waste. Oh yeah, Roman is noting, I should add, yeah, in the chat, there's an important comment from Roman, and see, let me get to the right place. I'll add a little more on the history. Let's see, let me copy this. Copy. There's a French inventor. Roman, I didn't realize there was a recent fight over that. That's been a long-standing one. There was a recent decision.
No, I don't think so. But I got the opportunity to discuss with Jean-Claude, and he mentioned a few weeks. But you know how it is, right?
Okay, but yeah, Jean-Claude, I probably maybe has the best claim to being the first to register. Ramon, I'll update this page to add a few of the different. There's a very strong nationalistic, different parts of the world claim that they invented 3D printing.
Yes, I was mentioning it as a joke, but it's true.
No,
at the same time.
but I should add a little bit more on that because yeah, and Jean-Claude has a strong argument. Good. Okay, so those are all good reasons for 3D printing. Now, let's see, this is a classic, Benchy is a classic 3D printing test problem. There are many limitations in 3D printing. A 3D printer is not like a 2D printer where you just push print. So a big limitation is you're going to see all of these. The most common technique you'll use extrudes a filament, and if things go wrong, you get spaghetti. Some of you might be using a technique where you fuse powder, and if things go wrong, you get earthquakes. Some of you might be using a technique where you expose a resin, and if things go wrong, you get goo. There are a number of failure mechanisms just within the printers. Second, the feature size is limited by the printing process. And for things like the resolution of the surface finish can be much lower than you can get with other tools we'll use. Time is a big one. Let's see, this is a link to let's see, an ad, but after the ad is a race to see how fast you can print Benchy. But on a typical printer for a typical project, it takes hours. Let's see, Ricardo is adding this link. Oh, I see. Yeah, that is a good summary. Typically, for a typical printer, for a typical design, it's hours. There's research on bringing that down, but it takes hours, and it's not unheard of to have a job that takes days. On the materials, open printers where you can use any materials, the cost have come way down, but commercial printers with commercial materials are very expensive. You can spend hundreds of dollars on a small print. So for the materials, these are two different tables of materials you can print that are convenient. And I'll talk about printing processes and printing vendors, about the trade-offs among them. There are a number of polymers, and I'd say out of all of them, polylactic acid, PLA, is the most common. But there are polymers that are harder, there are polymers that are flexible, there are polymers that are translucent, polymers that are soluble. Those are most common. There are fillers. I'll talk about printing processes. You can't directly print wood, and outside of a high end, it's much harder to print metal, but you can use fillers of these in other materials. So Jason is asking about carbon. So again, there's a lot of claims and counterclaims about the carbon process. There's a lot of research projects working on speeding up printing. That's very much a work in progress. Something to know is not all, but most of these materials are hygroscopic, which means they absorb moisture, which means how you store them matters. So you want to store them sealed. When you open them, over time, the qualities of the material will degrade. And I'll talk about that more in a little bit. Let's see, I'll talk about post-processing in a little bit. So this is a very important article. When you print, the printing process releases volatile chemicals and it releases microparticles. And so this is a really nice article. And there's two important tables here. This is the fine particle emission. This is a logarithmic scale, so each is a factor of 10. This is polylactic acid. This is a range of other materials, and then this is ABS. And what you'll see is there's a huge difference between the particulates between PLA and ABS. And then this table down here is emission rates for volatile organics. And again, this is PLA, and then this is ABS and other materials. And what you should take away from this is PLA is office friendly. You can sit next to it in an open printer and it's not particularly hazardous. But just about anything beyond that needs ventilation. You'd like to have an enclosed printer with a HEPA is a type of filter that filters the exhaust from it. Ideally, you'd like to vent it outside if you can, but you need to be aware of that. So behind me, I have a sealed printer with an environmental filter that I use in my office. In my basement, I have printers that are open where I print with other materials where I don't want to be breathing what comes from it. So you need to be aware of the printer as an environmental source. And that's one reason why I would segregate PLA printing from other kinds of printing. Next is a key thing is the design rules. So you can't send anything to a printer. These are images of a series of tests. You'll find many different test parts. This is just a series of test parts I did a few years ago. One test is you need to support the print. So probably the best example ever of this is, this was a beautiful project from a group, Nervous Systems, and they wanted to print clothing. And so what they're doing here is mathematically, they're lowering this into the print volume. And then after doing that mathematically, they send that to the printer and print it. But now to print it, you need to support the all of those links. So in this case, this was designed around a print process I'll describe, which is a powder bed. And so the powder bed supports all the links. But for any other printing process, you need to separately remove the support, which can be very annoying. Jason is asking about venting. Jason, this is similar to, it's not as bad as laser cutter venting, but it's in the same spirit as laser cutting venting. Again, it's not, there aren't quite as much volatile, but you don't want to vent it where people breathe it. So in research labs, you vent it to the roof with a high velocity fan shooting it up. Short of that, you want the vent away from where people can be breathing the exhaust. So for the supports, let's see, yeah, Ramon, you're noting PHA that's biodegradable. Yeah, and PLA is also plant-based. Okay, so coming back to the design rules. In each of these, I've got a FreeCAD file, I've got an STL, I'll talk about formats, and I've got a picture. So one test is overhang. So here I've got something sticking out, and then I need a support to hold it up. And so for FDM, which we'll talk about in a moment, you print a block in here that is designed to not quite adhere, and then you pull that out. So that's a test for overhangs. Then an important test is clearance. What I've done here is I've printed a series of rings, and I'm going down in steps by 1/1000th of an inch. And all of these released, but those, they got so close that the two parts bound to each other and I couldn't release them. So that's measuring how close a wall can be before it sticks to get a part that moves. Then ideally, other than something like a powder bed, you want to print without supports. Supports take more time to print, they create waste, and depending on the process, they can be difficult. When you learn about the design rules, you can learn to print surprisingly most of what you need to do without supports. So this is the most important one. What I've done is I'm changing the angle. And so this is just vertical, it's perfectly fine. This one, I'm coming out horizontally without a support, and I get spaghetti underneath it because there's nothing to hold that up. But this is in degrees. You'll see around 20 degrees or 30 degrees. That's enough. So each layer builds on the layer below it. So as long as you don't have flat surfaces, but just slightly angled surfaces, you can grow out without supports. So that's maybe the most important of the design rules. This one is testing how far out I can go horizontally. So a short distance I can go without supports. The further I go, the worse it gets if I try to make that unsupported. But that's immediately followed by this, which is bridging. If you look at here, I'm going a long distance without supports. And the reason for that is in what I'm doing, if I'm building up a layer here, and I'm building up a layer here, if I then start going off into space, if I stop, I lose, I get a mess. But if I can come over to here, I'm pulling the filament from here to here, and then I anchor it here. So that's called bridging. Bridging is where you pull between two places you've built up. And so, for example, if you have a house and you want to make a door, the roof here can be flat rather than my comment about needing an angle, because here you're bridging over the door. So as long as you're pulling between two anchors, you can span quite a long distance without needing a support. So that's bridging. Next is wall thickness. So here what I'm doing is, this is with, I'll talk about processes, a stereolithography printer. I'm making the wall thinner and thinner. And depending on the process, there's a limit to how thin the wall can be before it fails. And on the opposite side, I'm making the gap thinner and thinner until it gets so close that it closes up. So there's a limit to the thickness of a wall. This is a test where I just made a volume and I've set the outside dimension and the inside dimension. And depending on the print process, the actual size you get can be a few thousandths of an inch off of what you think you got. So when you're designing parts that fit together, you need to characterize the dimensions you get from the printer versus what you think. In theory, there's no equivalent to kerf. In theory, the dimensions are what you tell the printer. In practice, depending on the printing process, there can be some deviation between what you get from what you ask for. Most printing processes are anisotropic. So in this process, the layers are horizontal. And so the bottom piece here is strong if I pull it in tension, because I'm pulling on the fiber layer. Here, if you look vertically, if I pull this in tension, it's much more prone to delaminate between the layers. So the strength of the print depends on the angle of the print. This is just printing a sphere, and you can see on the side it looks nice and smooth. On the top here, you can see the steps because there's a flat angle compared to how I'm layering it. I'll talk about some ways to deal with that. Then infill is you can print a dense structure that's strongest but use the most material and takes the most time. Here I'm printing a completely hollow structure that prints fastest and is weakest. And in between, you can vary the density of the infill, which is around the parts you don't care about, how much you fill them in. And so that's trading off material use and printing time versus strength of the part. Then a final one is if you have a sharp corner, when you print that, what you'll actually get is sort of a mess there. And the problem is because you can only fit one layer of filament at the sharp corner, then two. And so you don't want to do that. You want to facet so that the printing can create a few solid layers to give you a sharp edge. You don't want to have a sharp corner. So all of those are design rules, and you want to design your design around the constraints of the printer to make a strong part with a good finish that prints quickly. You don't design an arbitrary part and hope the printer can do it. You want to learn your printer's design rules. And so the group assignment is to test the design rules. So I want to check how thin can a wall be before it collapses? How close can surface be before they touch? What's the dimension of the part you actually got versus the dimension you asked for? So you can run these. You'll find a number of different test parts for it. Next is the most common printing process you'll be using, and I'll talk about others, extrudes a filament. And the distance over the bed is critical. If the head is too high, it's printing in space and it doesn't stick. If the head is too low, it actually digs into the bed. So you want it to get that dimension just right. And further, the bed might not be exactly flat. So the right distance depends on where you are. So when you get close to it, if you print too close in side view, what you print is squashed very thin. If you're too far away, it's not even really sticking. And there's a happy place where when you print, it's just sort of slightly squashed to be the right distance. Let's see. I'll talk about non-flat printing shortly. Luke's adding this, which is printing with arcs to try to avoid overhangs. That's related to non-flat printing, which I'll talk about shortly. Setting the height of the printer over the bed is a critical parameter. When you set up a printer, you need to adjust that, and you need to get this happy place between squashing the print and not adhering. And better printers measure that each print. Cheaper printers, you set it and hope it stays right, but it drifts over time. Better printers, each print job, they characterize the print height and adjust it. Now, one of the other annoying things is, and one of the reasons for the failures I showed you, let's see, I'll talk about textiles shortly. You start printing, and if the adhesion here isn't very good, partway through the print process, it starts to come off and you get spaghetti. So how the print sticks to the bed is another critical parameter. One approach is to put glue on the bed, like a glue stick. I don't recommend that because that builds up and gets gooey and sticky. You want to keep the bed clean is one thing, from things like oils on it. And then something you can, there's two things you can do. One is you can print a raft, which is a layer designed to help adhere to the bed. And then you can print a brim, which is a lip that helps hold the part down. So you'll have to experiment with your printer and your process, but typically cleaning the bed and adding rafts and brims will help parts that as the part cools, it can bow a little bit, and that's part of what causes it to come off the bed. Once you're done, there's a lot of things you can do to post-process. So this is a resin, I believe this is epoxy-based, excuse me. And so when the print comes off, typically you can see layers from the printing process, depending on the print. This is a filler that you smooth over it that will give you a much smoother finish. There's a number of different materials you can use to do that. And then a really powerful technique is plating. And in particular, you can electroplate, which is the print in a polymer you can coat and then put it in a bath where you drive a conductor on it. So rather than printing a solid metal part, you can make what look like metal parts and have conducting surfaces by electroplating. And this isn't that difficult to do. The chemistry is not very bad for electroplating. So we get to printing processes. This is a good table. Shapeways is one vendor that maintains every kind of printer. And so in their list, they list examples of output from lots of different types of printing processes. Oh, sorry, yeah, Ricardo mentioned about annealing. The, let's see, for the FDM style printing, you're printing into, with the material just above the bed, into a temperature just below it. Better FDM printers have a heated volume that takes care of the annealing of the part. Generally, annealing is less relevant for FDM printing. It's essential for things like the powder printing I'll be talking about shortly. So yeah, let me fill in as I talk about these. So stereolithography is one of the first processes. 3D Systems was a developer of that. In that, you have a bed of a resin, and then you have typically a laser you scan, and where you spread a layer of resin, and where the layer hits it, you fuse it. So stereolithography is I'd say the highest resolution of the printing processes, because you're printing down to the resolution of the focus of the laser that can be micron resolution. Originally, they scanned lasers. Faster ones use digital laser micromirrors to do parallel exposure that it typically isn't quite as high resolution, can print quicker. So STL has a limited range of materials, but is great for high resolution. Fused deposition molding was developed by Stratasys. FDM refers to that process, fused deposition molding. There's a few other terms that get used because they consider that their term, like FFF for this. In these, what you're doing is you have a nozzle, and the filament goes into the nozzle. It's just above its melting temperature. And then it comes out, and there's a heated bed that's just below the melted temperature. And ideally, you're also in a sealed chamber that's just below the melting temperature. And so it comes out, but it sticks, and it stays where you put it. And so these have extruders. This is an article on a smaller extruder lets you print more finer features. A bigger extruder lets you print more quickly. And there's been a lot of work on optimizing using a bigger extruder, but controlling how you use it to get the best of both of those. In the family of these, generally you're extruding polymers, but you can extrude other materials. These are colleagues at Berkeley that have printers that extrude clays to make these sort of beautiful objects by extruding clay. This is a colleague at USC that extrudes concrete to make buildings on really big scales. So FDM is the most common process. It's likely what you're going to use. It's not the highest resolution. It's not the fastest, but it's low cost, it's flexible, and it has good structural properties. This is an emerging process where, and this has various names. In this, what you do is instead of extruding plastic, you have, for example, a little plasma torch, and you extrude a metal through it. And so it's like FDM printing in plastic, but you use it to write with metal. And so that's one of the metal printing processes. So yeah, Jessel, you can get set up in a fab lab to do electroplating. And again, Formlabs has a good, the link I showed before is about getting set up to do it. Electroplating isn't kitchen chemistry, but it's not hazardous chemistry in a hood. Formlabs has a good page on getting you started with electroplating. Inkjet binders, this is a link to 3D Systems bought Z Corp, one MIT spinoff. Here what you do is, and actually HP has a related one. You spread a layer of powder, and then you print an ink that binds it together. That's great because these powder bed printers are the winner for support, because you spread a layer of powder, and then you selectively sinter it together. Then you spread another layer, and you selectively sinter. And the unsintered powder supports the rest. And so they automatically make the supports, and you just take out your part. Now, the inkjet approach is, let's see, friction stir welding is an important welding technique. I'd never heard of friction stir additive. Oh, that's interesting. So
you take a bar of material and turn it really fast, and
yeah, so friction stir welding
use it to build up a part.
Yeah, friction stir welding is a crazy sounding thing where if you want to join two materials together, you just bring in a head spinning really, really fast, and you smush them together. It seems like a really crude idea, but it's among the strongest welded joints. But I had never heard of it being used to deposit material as an additive process. That's interesting. That sounds very promising. So the inkjet approaches, what's good about them is there's no supports. And what's also good is you can print in color with them. What's bad is they're weakly fused. So these need post-processing. These need annealing or infusing. You need to do something to strengthen the joints. Polyjet is one of the nicest processes. This is from Stratasys. And what this one does is it inkjet prints little droplets of material and then fuses them when optically. And so this process, and I'll show examples shortly, is very high resolution. And then it handles multiple materials, which can vary structural properties or color. The limitation in this is it's very expensive. The machines can cost hundreds of thousands of dollars, but this is among the highest resolution and highest performance. This was an interesting side corner. This is a printing process where you, I guess this one is obsolete now, but you would print sheets of paper, cut them out and glue them together. They looked great. They had terrible structural properties. Looks like they're no longer in business. So I'll drop that. Then laser sintering is where you spread layers of powder, but rather than printing, you use a laser to fuse it together. And so this is used in the highest end metal printers, and these cost $1 million. But it's also becoming accessible in laser fusion printers that are not millions and not thousands, but tens of thousands that I'll talk about. Two photon printing is where instead of using one photon, the link looks broken. I'll fix their link. Yeah, these happen when people update their sites, but Nanoscribe, I want to show you images of their printing. What they do is nearly nano printing. So by using two photon printing, there's a resolution enhancement at the focus of the laser. And so this lets you make prints with features that are microns, millionths of a meter. And then this last link is, and there's been a lot of work since then, but this was a meeting I ran looking at not printing, but assembling and disassembling. And so research on micro assemblers rather than printers. And this is promising to make high performance functional systems. So let's look at the machines now. RepRap was started by a dear colleague, Adrian Boyer. And Adrian's interest wasn't really 3D printing for the masses. What he wanted to do is, let's see, what he wanted to do was make a printer that can print a printer. So this is an article on self-replication. And Adrian famously, I think that there's a picture in here of had a printer then print the parts of, yeah, you know, this doesn't show the picture I'm looking for, but had a printer print the parts of the next printer. And so he was very interested in how a printer could make as many of its own parts. Charlotte, yeah, so for bioprinting, it's not done typically with inkjet, it's done with syringes. I'll add a link to, and my lab's done a lot of work on this. There's bioprinters where you have syringes that put out gels that are medium cells grow in and extrude gels. So typically those are the syringe type printers. So RepRap started an open design for a printer aiming at printers that could print a printer. And many projects spun off from that. So Ultimaker started at Fab Lab in Utrecht in the Netherlands. And they did a lot of work to optimize the print speed, to reduce the moving mass, to get it printing as quickly as possible. They did a heroic, wonderful project to make a full-size elephant. And they did it by mounting printers on gantries so that as the printer prints, the printer itself lifts away. And then they made a whole line of these printers and printed a full-size elephant. I think it took about a month to do, but printed an elephant. Prusa then has done a really good job of taking the lineage of tracing back to the RepRap, refining the design and occupying a really nice sweet spot. The Prusa is an open design. You can download everything, but you can buy it from them in kit form at a reasonable price, or you can buy it from them in a finished form. And so they've done a really good job of that. And so that's a classic FDM printer. It's very easy to configure. It's very easy to optimize. It's very reproducible, reliable. These are those test parts on a Prusa printer. SaneSmart are Shenzhen colleagues, and they've taken that lineage, and they've done a good job of just dramatically cost reducing. And so they've brought printing costs down to hundreds of dollars with nicely optimized printers. The earliest ones didn't measure Z position, and as a result, were fairly unreliable. They've now tuned that in. One of the things they make that's really interesting for the labs is they make moving bed printers. Let's see, I'm adding a link. They make this moving bed printer. And so the original reason for that was you can keep the printing running overnight and the parts just fall off at the end. But one of the uses we found for this is you can have a take-up roller and you can just keep the printer running and you can print long extrusions. So if you want to make a machine, you can print machine parts bigger than the machine. Hank is also noting Voron, which is aiming to take this lineage and optimize it. Hank, what have you decided about this after working on building yours?
It's almost ready.
Okay.
So I did that time after the boot camp. So Sako is now making the last parts.
Okay.
And I hope will be working in the next couple of days.
Okay, I'll be interested in the report. It's been a long build.
Also, I added a link about the 1 meter axis we made at the boot camp.
Oh, that's great. So this was, he mounted this vertically and then just started it printing and printed out this long axis from the moving bed. Yeah. This was a great example of bugs that are features. Hank didn't have a place to put the printer, so he decided to stick it on the wall, and it had the benefit that it comes out. It bows a little bit as it comes out, but he was able to print this. How long was the axis?
1 meter.
Yeah, so be able to print a complete meter axis. Nice. Sindo is an interesting company. They make 2D printers, and they took 3D printers and productized it. And so let's see, Jason is asking about Naomi. I don't know the history. I'd be interested if you know more about the history. The SaneSmart, what's nice about these is they're completely sealed, and these are not designed for tweaking, but they're much more user-friendly in that you just push in a cartridge, you push print, and it pretty much adjusts anything. This is an emerging multi-material printer to add multi-material printing to other printers. Then Formlabs is a company that was spun off from my labs, one of my students, Max. And Formlabs, their goal was to improve resolution for everyone, to bring down the cost of high resolution printing. So their main product is this, which is a stereolithography printer. And this is what the test parts look like on that. And so if you compare this to what I was showing you before, what you'll see is the feature size is much finer and the surface finish is much better than FDM printing. This is a documentary about a famous fight they had with 3D systems, about the emergence of it. That's Max and David inventing it. And they've done a number of interesting projects with it. This is one I love. This is a 3D printed stop motion movie. Oops, let's see. It didn't like it when I made that full screen. A 3D printed stop motion movie, and every frame of the movie is a print. So they printed huge numbers of parts, and every frame of the movie is a print. So really beautiful project with it. And then one of their most recent projects is they're mass producing characters. So with Hasbro, you can buy a superhero that's you. And that's done by having a big print farm mass producing individual characters. And then more recently, they've come out with a laser sinter system. And this is $30,000 range, not $1 million. This doesn't do metal. It does typically nylon, but the nylon can be glass or carbon fiber reinforced. So it makes dense parts with good structural properties, pretty good, but not fabulous surface finish, a little bit rough from the powder. And the real attraction of this is, aside from the good structural properties, is because of the powder bed, they can be essentially arbitrarily complex. You can make tremendously complex parts, and you just sort of reach into the bed, pull it off, shake off the powder, and then blow it off and blast it off. And so this is more than an entry-level printer, but like in the super labs, we're adding these for laser sinter. Then Stratasys has this machine. Ooh, that's another broken link. So the J55 is one of my favorite printers. This now costs $100,000, but in return you get this. So it prints with jets of material. The jets can have different colors. And so this is 3D scanning a shoe and printing a shoe. This is printing this with the channels for the microfluidics. And all of these aren't color on the surface. They're actually volumetric color. And so it really does gorgeous color printing. Ohad, are you on the call?
I am.
Yeah. Can you talk about your role with Stratasys and just your thoughts about 3D printing?
So now I'm in charge of innovation and sustainability at the company. So I believe in multi-material printing, and this is what this allows to do. Recently, we have the ability to print air as well and print on fabric and other things. So it's kind of disrupting the different industries. But I think that 3D printing, it still didn't reach to the point that we can use it daily, although we can see that in many industries. And
Yeah,
multi-materials and multi-processes maybe can take it to the next
this
direction.
is currently the highest performing process. Right now, it's $100,000 scale. This hasn't yet been turned into DIY consumer machines. That'll come in the coming years, but we're still a few years away from DIY versions of this. But we're putting this into the bigger kind of super labs.
Mm-hmm.
Good.
And I put a link for a full stop motion movie by Leica that is fully 3D printed.
Oh, another.
And also Kobo, they did the movie Kobo was like all figurines were 3D printed.
Cool. Okay,
So,
I'll add links to these. Beautiful. Yeah, and any questions? Ohad's a great resource on 3D printing. Then in the this is a site associated with the machine building class I teach. There have been a number of printers done in that. Danielle and Gracia, Fab instructor guru is developing versions of printers. This is a really neat version of a printer where instead of having a fixed gantry, you put it in a room and suspend it. All of these are open designs, an interesting part of parameter spaces. Carbon, Jorge is asking about carbon. My list here isn't exhaustive. Each of these is a different part of parameter space. Compared to carbon, I like the Stratasys polyjet process because it does a really good job of multiple material properties for these sort of higher end printers. Precious plastic is the opposite. This is a really nice project with open designs, and let's see. And what they have is a series. Let's see I want to see the machines. Sorry, their site. Here, sorry, this is the link I want. So they have a series of open designs of machines, and what this is aimed at is taking recycled materials, grinding them up, and then turning them into filaments to make your own material. This is another project this is a nice resource to be able to make your own filaments from materials you source, as well as the other parts of the printer. So those are interesting. Again, this isn't all of the machines, but these are interesting parts of the machine space. And also, all of these in some way have strong connections to the Fab network. We work very closely with them. So then for materials, this next group, these are all vendors of filaments. And they have a great range of them that are rigid, flexible, translucent, colored. This is a filament. It's tricky to print, but you can print and then melt away. So you can do metal casting. This is a link to a foundry process to do metal casting. And then it's really easy to print on fabric. This is an example of if you put fabric in the bed of your printer, you can print on fabric as the bed. And that has lots of fun use cases. And then beyond that, this is a link to you can actually print fabric. This is a student in my lab who developed a really nice process to under extrude. And by doing that, you print fabric. And not only that, he set, I think, a record. He did a print job that took a month. And when you took the print job out and unrolled it from the printer, it was the size of MIT's biggest sports field. So that's actually printing fabric. Then food. You need to be careful with food. So this is a link from Formlabs. This is a link from Prusa. This is a Hackaday study. There are a bunch of issues with food. Printing food safe is like being kosher. The whole chain of producing your material, your printer, everything has to stay food safe. So this is a link to materials that are food safe. And then something else you need to be aware of is when you print, if the print has lots of little ripples from the print layers, food can get stuck in them. And so you want to print with surface finishes that don't trap food. So these are two good links on what you need to know about food safe printing. Then you have, and you'll use printers in your lab. Something I recommend is Prusa makes many of its prints, many of the parts of its printers on its own print farm. They've got this massive print farm of Prusa printers. And My lab has a more modest one, but I have maybe 10 or 15 of these. And with printers coming down to hundreds of dollars, for a few $1,000s, you can set up a print farm. And once you've done that, how you use the printer, I find, changes. Once you have sort of unlimited printers, you think less about the time of the print job, and you do more ambitious things in the printer once you have a job you can send them out to. And then these are all vendors I mentioned who manage not just print farms, but many different sort of printers. And so the $100,000 printers and the $1 million printers, you can send jobs to them that are much more expensive than doing on your printer, but you can get access to printers you wouldn't otherwise afford. Okay, so now you need to send a job to a printer. Far and away, the most common format is STL. Dates back to not Stratus, 3D Systems at the birth of stereolithography. It's just a list of triangles. And so that's what's good and that's what's bad. It's very easy to open and read an STL file. There's no conversion issues. What's bad about it is it's missing all sorts of information. It doesn't know about different materials. It also doesn't even know about units or dimensions. It's just a simple, dumb format with triangles. But what's good about it is if you like coding, it's very easy to write. So your assignment is going to be to make an object that you can't make subtractively. So if you had a 5-axis machine tool, you could come in and cut. What I want you to do for this week is make something where you need to get access to internal features that you couldn't do by cutting away. And the assignment for this week was done by Ling Dong, an incredible student. So this is his homework for the class. And you can clearly see how it's not something you could make subtractively. But not just that, all of the code to make this is on this page. And so he's a good programmer. And so each week in the class, rather than using a CAD tool, he wrote a program. And so all of his code to do it is on the page. And this was done with one of the Stratasys PolyJet printers with a soluble support to make this incredible part. So if you like coding, you can write STL files directly. Beyond that, Pleiades color. This is an emerging format that's been emerging for many years to deal with the limitations of STL. And what's good is it's more general. What's bad is the committees behind it put in everything they could think of. So it's beginning to settle, but it's like a container format of formats. OBJ is an Autodesk format, but it's a convenient way to convey colors to printers. Then these are all 3D graphics formats used for graphic interchange that things like color printers increasingly can handle. Advanced printers like the Stratasys ones, you can talk to them with voxels rather than triangles. So you actually talk to the individual volume elements, and that's great for really complex geometry. Then the most common way commands are set to the printers are G-codes. We're going to learn more about that in Machine Week. But one of the things you can do with G-codes is you don't have to print in flat layers. And so something that's an emerging research area is by moving all 3 axes at once, you can make smooth surfaces and print more efficiently than just slicing in layers. And so non-planar printing is really still a research area, but it's beginning to get deployed. Okay, 2 more topics, software and then scanning. So first, you need a tool like MeshLab is an example, NetFab Mesh Mixer. All of these are tools just to deal with meshes. Unless you're doing voxel printing, you'll be sending meshes to the printer. And so they let you inspect your meshes, edit them, filter them. Just there are a number of different operations you end up needing to do on meshes. So you want to have a good mesh tool. Then you need to slice. And so slicing is taking your design and turning it into print commands. And most of you will be using FDM printers. There you're setting the path of the head. If you're using an STL printer, it's the path of the laser. If you're using a powder bed printer, again, it's the fusion path. All of these are slicers, and the good story is they've all matured. They've all learned from each other. So any one of these, like say Cura came out from Ultimaker. Prusa Slicer is Prusa's version of the Slicer project. All of them do pretty much everything I'm describing. So they let you specify bed adhesion. They let you trade off print speed versus time, pick the infill, pick different types of infills. And increasingly, they have different strategies to deal with things like the overhangs and the supports. They let you grow supports that are pretty easy to remove. So the printer you're using typically comes from one of these families, but they're all pretty converged. I'll do a pretty good job of that. Then to send it to the printer, if you're using an open printer design, this is a nice open project to send jobs to the printer. And then this is a nice project. Once you have more than one printer, this lets you build interfaces to control multiple printers. Let's see, there's a question in the chat about who bought who. So MakerBot was bought by Stratasys, and that wasn't right. Wasn't Ultimaker also recently acquired by Stratasys?
We merged them.
Okay.
So now they are like a sub company of Stratasys, but we merged them.
Interesting. Yeah, I mean, there was a lot of overlap between them, and so that sounds like a big convergence. Okay, and then Michael's asking about splitting a big model into smaller models to assemble. I don't know any way to automate that because, I mean, it's very easy to just slice it into chunks, but designing the features to fit it, comment in the chat, anybody else, but I don't know a way to automate splitting a big model into smaller parts.
Magix can do that.
What is that?
Magix.
Sorry, help me find that. I'm not.
It's by Materialize Magic down there.
I see, interesting. Okay, and then the last thing is, these are all sites that let you share your designs. And in particular, all of these have ways to embed it into your site. So these let you share designs, but they also include viewers. So you can embed the viewer into your site and see the model. And like, this is not a commercial platform. This is just a nice website extension that lets you put 3D content in your site and embed a viewer for that. So those are for sharing the sites and being able to view it. Okay, last 10 minutes is going to be on scanning. Scanning is exciting and frustrating. Scanning is taking a 3D object and getting it into the computer. There's no perfect way to do it. So typically you get a cloud of points, then you need to triangulate it to turn it into a surface. Typically it's not watertight, meaning there's holes, which means the printer can't print it. So you need to make it watertight. And often you want a texture to be able to represent how the surface looks, as well as the geometry. See, Blair has another link. Let's see, this is Blair, is this another tool for printing big things?
Yes.
Okay.
It's Larry Sass was involved in developing that one. Yeah.
Oh, interesting. Okay, I'll add links to these. So 3D scanning, it can be strongly dependent on how your object is lit. It can be strongly dependent on the materials. It can be strongly dependent on the texture. The ideal tool to do it is, my lab has $1 million X-ray microscope. And so this is a fly-through of the head of a housefly. It actually gives you the inside as well as the outside at micron resolution, but is $1 million machine. One way to scan is by scanning a probe over the object and tapping it to feel the surface. A nice way to do it is optically, and this hasn't yet been done for a consumer version, but I think it's in the future. Here you scan a focal volume with the microscope, and you see where the focal volume hits the object. So it lets you scan the object without having to physically touch it. If you can afford to destroy the object, you can mechanically slice it. So this is an article working out the wiring of brains, and it's done by, in tiny little layers, removing a slice and then taking a picture and removing a slice. Opacity is where you make the object disappear, colloquially called a milk scanner. You pour an opaque liquid over the object, which could be a person, and you watch it as it gets submerged, and you trace the boundary from that. Digitizer arms these don't automate the scanning, but what they do is they let you measure particular points. And for example, in Frank Gehry's shop, the architect, when he designs a building, they take his designs and they don't want to scan everything. They just want to scan the relevant parts of the design. And so this has a human in the loop, and it's not an automated 3D scan, but you add value in measuring just the parts you want. Then let me come back to, actually, yeah, let me stop on this. So photogrammetry is where you take a lot of different pictures and then you combine the pictures. And so these have been exploding. So Alice Vision is an example of one of them. Meshroom is an example of another one of them. These need fairly substantial computing. So I've got some links to doing it in a cloud. And so here's an example of, I took this vise. I'm intentionally putting it on the carpet. And I'm using the carpet as the background because it has a lot of texture for the scanner to see. And I've got it lit fairly uniformly, so there's no shadows or bright lights. And then I just took a lot of pictures. And then you throw this at this tool. And then what it worked out here is it figured out where I took all the pictures from. And then it gave me a 3D model of the object I scanned. Now, you'll see the 3D model is pretty good. It got most of it, but it's not exact. It missed a few parts of it. So photogrammetry, depending on what you're doing, gives you a good model, but typically there's some cleaning you need to do. So these are all versions of photogrammetry software, some commercial, some open source, some that run on your phone, some that need the cloud, that just start by taking pictures. Speckle is, rather than just taking pictures, where you put a dot pattern on it and then use it. And so historically, the Kinect was an important commercial product that did it. And then Reconstruct Me is scanning software for that. Lasers are where you raster a laser and you see where the laser hit it. And Fab Scan is an open project to make a laser scanner where you aim the laser and then you look to see where the laser hit it. Structured light is where you project a pattern on the object and you look at how the pattern deforms. And so let's see, this is an example. This is an example I did a while ago where what I'm doing is I'm using a laser projector, a little pico projector. I'm putting out lines, and then I look at how the lines bend on the object, and then you can combine them to get the math of the object. LiDAR is where you measure the time of flight for a laser to go and come back. And with a single laser, you rotate it around. But there's a number of emerging products, and everybody keeps buying everybody in this world, where there are cameras where each pixel in the camera, instead of measuring light, actually measures the time of arrival of light. And so you send out a light pulse, and then it gives you a depth map. And these are really being driven by phones. For augmented reality, we'll talk about later, there's a tremendous need now for phones that can measure 3D geometry. So right now, these are in rapid flux, these 3D imaging cameras, but they give you one projection, and then as you move it, you can pull a scan from that. Then light stages are, I'd say, the most powerful kind of scanning. The biggest light stages are a room full of lights and cameras. And this is a colleague, Paul Depovec, who's done beautiful work on light stage scanning. And he did this wonderful project where he made a tabletop version. So what he's going to do is, this is a ring of LEDs, and here's a shiny object that's hard to scan optically. Then he has an array of cameras here. He's going to spin the camera around, spin the lights around, and he's doing what are called spherical harmonics. He's putting out a range of illumination around the volume around this object. Then the cameras look at all of the reflections. So what he's doing is he's lighting it from many different directions, not just one direction. Then he does interesting math. And if you want to do computer graphics, you need to separate specular from diffuse scattering. You need to separate surface from subsurface scattering. You need to describe the texture of the material. And so by rotating the object and the light source, he measures what are called light fields. And so he's not just measuring the geometry, he's measuring the full optical scattering properties of an object. And then once you've done that, it then lets you separate all of these, and it lets you completely re-render the object photorealistically. And so these are used in Hollywood special effects to digitize a person and make a photorealistic actor. That's the highest performance. And then finally, the last one I'll mention, and this is a very active research area, is what's called SLAM, which is simultaneous localization and mapping. And so this is, once you have photogrammetry or a depth camera, as you move around a room, what it's doing is it's continuously building a map of the environment you're in. And again, that's really being driven by augmented reality that we'll talk about in later in the cycle. So you should take away from that, there are many different types of, oh, let's see, sorry. A link I skipped over is, these are low-cost structured light scanners. So for entry-level 3D scanning, these do structured light with a built-in app. And so this is a good kind of just entry-level scanner. Versus, let's see, I don't have it here, the this is a $30,000 laser scanner with GPUs built right into it. But something like this is a good, just completely built-in entry-level scanner. Yeah, there's Quentin, for his final project, made a photogrammetry 3D scanner as a final project. So take away from that, there is no ideal solution to scanning, but there are a lot of interesting options to experiment with. And there's lots of room to develop these in your lab and extend them. So as a group, characterize designer rules. Yuichi is adding a link to his lab scanned. Nice. Okay, then individually, the scanning object is just scan any object. You know, optionally, you can print it, but scan it. Then I want you to design an object. Make it small, only a few centimeters, because you're going to be limited by time on the printer. And the design challenge is make it so you can't make it subtractively. So it has to have revolving parts, nested parts, overhangs. It's an exercise in creating geometry that you couldn't just do with a milling machine. And you know, think ahead to your final projects. So it can be as simple as a case for part of your final project, but it can involve, for example, tabs or nesting or features to snap the case together as part of the design study. Okay. So then you're going to print this week, and there is a recitation on Monday, and this is going to be an intro to programming. You don't need this if you're an expert programmer, but for beginners, this is just going to be across all the languages we're using an introduction to programming. And then next week, we'll go back to electronics where you're going to design your own dev board. So by the end of this week, you should appreciate the strengths as well as limitations of 3D printing. And I'd say even more so strengths and limitations of 3D scanning, but be comfortable going from digital to physical and physical to digital that way. Okay. Happy printing. See you all in a week. Bye-bye.
Bye.
Bye.
Hasta luego.
Gracias.
Masalama.
Bye bye. Hey, so.